Hello everybody, this is Team C9, or WinRAR, of The Ohio State University's Fundamentals of Engineering Honors Robotics Competition. And this is just the first design update for our robot, and I hope that we can keep this as a sort of weekly series to document the robot's progress and also demonstrate some of the robot's features, and as well as go over some things that might have went wrong during the last week of testing. So the first thing I wanted to talk about was the heart and soul of our robot, the FEH microcontroller. So this is basically a tiny computer that is very portable and versatile. This was specifically designed for Ohio State Honors Engineering students, and it has a variety of features. For example, it has an LCD touchscreen, as well as many input-output ports for the variety of sensors that will go into our robot, as well as some motor ports back here. So you can see the two terminals that we have for our two motors at the moment. So when you press the on button, it quickly turns on, and whatever C++ program we've uploaded into this robot will be executed as soon as we turn it on. So I've disconnected the motors because we don't want the robot running away from us. So the next thing I wanted to talk about was the drivetrain of our robot. So this robot is rear-wheel drive, powered by two Iguan DC motors. So FEH students were offered many choices of motors for use on their robot. For example, there were various servo motors that could be hacked, quote unquote, to work like DC motors, as well as conventional DC motors. Now these Iguans are actually the most expensive motors that were offered to us. However, our group chose these motors because while they were the most expensive, they were the only motors to have shaft encoders built into them. Now shaft encoders basically measure the amount of rotation that each motor is generating. So this is very useful for autonomous navigation for a robot, because obviously we cannot control it as humans. So the FEH microcontroller Proteus knows exactly where the robot is and how far it has to go. So we also have two caster wheels at the front. These are obviously unpowered, and they basically function like any wheels that you have on office chairs. So they have complete 360 degrees freedom of motion, and we chose them because if the robot had fixed wheels, it would be much harder to turn, and the turning radius would be much smaller. However, if we have these relatively low friction and free rotating wheels, the robot would be able to turn very easily. So let's talk about the chassis itself. It consists of a 6.5 inch by 6.5 inch sheet of laser cut, 1/4 inch thick MDF plywood. So the advantages of plywood over the other materials we were given, such as acrylic and aluminum, is that this wood is very cheaply laser cut, and it is also available to be manipulated after the initial cut. So we can screw in as many holes as we like whenever we want to, without compromising the integrity of the wood. So this would be a problem for something like acrylic, because after you laser cut the acrylic, you can't drill any more holes into it or make any other modifications, because it would make tiny cracks in the acrylic and the structural integrity would be compromised. So let's take a quick look at the side profile of our robot. So these two rear powered wheels are 3-inch diameter Dubro wheels, and these caster wheels are 1 inch in diameter. So one thing that is very apparent is that with our first robot design, the robot has quite the tilt. So the robot is mounted quite high in the rear and quite low in the front. So this was due to our initial design being a little bit different. We weren't quite sure exactly how far up the ground the motor mount would make the robot, or the rear of the robot. And we thought that these two caster wheels would also be a bit taller, so the robot would be a bit more level. However, there is a relatively easy remedy to this situation. So what we're going to do in the next few days is screw a few more sheets of this wood to the base of these two caster wheels. So both sets of wheels are going to be at the same level. However, the actual chassis of the robot is going to be a bit higher. So it'll make the front of the robot a bit higher off the ground, and it'll make our robot a lot better at doing further tasks. So let's take a look at the top of our robot. So these two components are micro switches. So you can press them relatively easily. So as the robot drives along this way and it hits a wall, both switches are triggered, and that's a way for the Proteus to know, hey, we hit a wall. We should probably stop rotating our wheels. So these two switches are go into the input and output ports right here, and this very crude cardboard structure is for hitting a button. So we have a performance test that the robot successfully completed where it had to start the course, go up a ramp, and hit a button, all on its own. So this structure was basically so that the robot could hit the button because it was placed a little higher off the ground than the front of the chassis was. So we just needed something quick and easy to hit the button. So obviously for our final robot design, we're going to have to make something more permanent, and that will be discussed in the next video. So let's take a closer look at the wiring of our robot. So these two sets of blue and green wires right here, they are for the micro switches, and they go into these input and output ports. These two sets of red and black wires are the power for the Iguan motors, and they get plugged in right here into the motor ports. These two sets of multicolored wires are the input and output ports for the shaft encoders for the Iguan motors. And finally, this tiny set of scarlet and gray wire, that is for the CDS cell. So let's take a closer look at that. So if we flip the robot, and you see right here, this is the CDS cell, or cadmium sulfide cell. So this helps measure light. So it helps because the robot will have to start the course when a light under it turns on. So this cell, the CDS cell, measures light levels and also the color of the light. So the robot can start when the light turns on. So let's talk about what went wrong in the last week with our robot. So we had a very successful first performance test. However, there were a few defective parts with our 3D printing. So if we take a look at the underside of the robot once again, and you look very closely, there's a 3D printed mount for the Iguan motor itself, the Dubro wheels, as well as this black adapter for the Iguan wheels, or for the Iguan motor to the Dubro wheels. So we initially got two of the same part, except they both simultaneously broke. So you can see that there are teeth, around 8 of them, that are featured all around this adapter, and they go into the plastic part of the wheel here. Except they all broke off mysteriously, or most of them broke off mysteriously. So we're not too sure what happened. Some of our TAs said that a lot of other students had trouble with these breaking Iguan mounts. So they also noted that all of it was blue plastic that broke and not the black plastic that we see here. So maybe it was a bad batch, maybe we incorrectly put it in the wheels, who knows. And also, one of the new adapters that we got was functioning fine, and the other one had the hole for the motor shaft to be a bit too big. So all we did was just put some super glue on our Iguan shaft to fuse it to the wheel here. So it shouldn't be much of an issue with the rotation anymore. So that concludes this video. It was basically an introduction to our robot design, and also the first design update, now that our first performance test is done. In the next few days, I'll post another video where we show off the robot with its new improvements, as well as some new features. So what can you look forward to? We're going to, first of all, remove this very crude structure and replace it with something more permanent to hit the button. In addition, we're going to be developing our paw system. So somewhere in the middle here, we're going to put a servo motor, and attached to the servo motor is a rod that can move up and down. And on that rod will be a paw mechanism. So it's basically going to be shaped like this. It'll have 2 prongs, and those 2 prongs can do many of the robot tasks for the competition. For example, it has to catch a lava lever and pull it up. In addition, it has to grab a lava sample and then bring it back to another location. And finally, it has to hit an antenna and move it. So all of these will be accomplished by the paw, and hopefully that will be completed in time for the next performance test. So until then, see you guys later.